In this lecture, we are going to talk about the four fundamental subspaces of an m by n matrix. Consider a matrix A, which is m by n. This matrix has n columns, A1, A2, all the way up to An, and each of these columns is inside of Rm. The four fundamental subspaces of A are the column space, which is the span of the pivot columns, the row space, which is the column space of A transpose, and that is the span of the pivot columns of A transpose, the null space, which is the vectors x such that A times x is equal to 0, and finally the left null space, or the null space of A transpose, which is the vectors y such that A transpose times y is equal to 0. Notice that the column space is a subspace of Rm, the row space is a subspace of Rn, the null space is a subspace of Rn, and the left null space is a subspace of Rm. We can also talk about the dimension of these four subspaces. For example, if we have a matrix A, which is m by n, with rank R, then the dimension of the column space is simply equal to R. Similarly, the dimension of the row space is also the rank R. Whereas the dimension of the null space of A is n minus R, this is in reference to the number of free columns. There is a total of n columns and a total of r pivot columns, meaning n minus r free columns, which means that the dimension of the null space is n minus r. Finally, the dimension of the null space of A transpose is m minus r, which is the number of free rows in the matrix A, or the number of free columns in the matrix A transpose. Let's now consider an example where we would like to find a basis and the dimension of the four fundamental subspaces of the following matrix A. Our first step is finding the first pivot position. In this case, it is the number 1 here. Then we use this pivot position in order to remove everything below it. Here we already have a 0 in the second row, however we have a 1 in the third row, so we are going to subtract one copy of the first row from the third row. The result is the following matrix, where the first row has not changed, the second row has not changed, and the third row became 0, 0, 0, 1, 2. Next, we are going to find the second pivot position, which we go to the second row, and it's going to be this one right here. We are going to use this one in order to remove everything below it, specifically this one from the third row. So we are going to subtract one copy of the second row from the third row. The result is a matrix in row echelon form, or reduced row echelon form right here, which has two pivot positions, this one and this one, from the first and second rows. This means that this column and this column are pivot columns, whereas the following columns are free columns. Since these three columns are free, it means that x2, x3, and x5 are free variables. In order to find basis for the column space of A, we're going to look at the pivot columns, the first and the fourth column in the reduced row echelon form of A, and we go back to the original first and fourth column in the matrix A. Therefore, a basis beta for the column space of A is equal to the two vectors 1, 0, 1 and 0, 1, 1, which are the pivot columns of the original matrix A. Since there are two vectors in the basis, this means that the dimension of the column space of A is simply equal to 2. In order to find a basis for the row space of A, we are going to look at the non-zero rows in the row echelon or reduced row echelon form of A. That is this row right here and this row right here. So the basis for the row space of A is the vectors 1, 3, 5, 0, 7 by copying the first row, and 0, 0, 0, 1, 2 by copying the second row. Since there are two vectors in the basis, this means that the dimension of the row space of A is also equal to 2, same as the dimension of the column space of A, which is simply the rank of A. In order to find the basis for the null space of A, we should solve the system A times x is equal to 0. This is equivalent to solving the system R times x is equal to 0, where R is simply this matrix, the row echelon form or the reduced row echelon form of A. We first consider the first row of R, which tells us that x1 plus 3 times x2 plus 5 times x3 plus 7 times x5 equals 0. This is the same as saying that x1, which is our pivot variable, is equal to minus 3x2 minus 5x3 minus 7x5, which are our free variables. In a similar way, the second row of R tells us that x4 plus 2 times x5 is equal to 0, which means that our pivot variable x4 can be written in terms of the free variable x5 as minus 2 times x5. Now let's take these equations for x1 and x4 and write the solution for the null space of A. So the solution vector x can be written as x1, x2, x3, x4, and x5, where x1 is taken from this equation, and it is equal to minus 3x2 minus 5x3 minus 7x5. x2 is a free variable, so it's itself, so is x3. x4 is minus 2x5, and x5 is itself. We can split this up into 3 vectors, one that is multiplying x2, which has entries minus 3, 1, 0, 0, 0, one that is multiplying x3, which has entries minus 5, 0, 1, 0, 0, and the last one, which is multiplying the free variable x5, which has entries minus 7, 0, 0, minus 2, and 1. Therefore, the basis for the null space of A is constituted of these 3 vectors, which are minus 3, 1, 0, 0, 0, minus 5, 0, 1, 0, 0, and minus 7, 0, 0, minus 2, 1. And therefore, the dimension of the null space of A is equal to the number of the vectors in the basis of the null space of A, which is 3. In order to find the basis for the null space of A transpose, we are going to solve A transpose times x is equal to 0. In other words, we are going to solve the row echelon form or the reduced row echelon form of A transpose, multiply that by a vector x and set that equal to 0, and we are going to find all such vectors x. In order to find A transpose x equals 0, or the reduced row echelon form of A transpose times x is equal to 0, we first find A transpose, which is given right here. Our next step is going to find the first pivot position, which is this one right here, and we are going to use this one to remove everything below it. We are going to remove this 3 by subtracting 3 copies of the first row from the second, remove the 5 by subtracting 5 copies of the first row from the third, and remove this 7 by subtracting 7 copies of the first row from the last, which gives us the following matrix. Our next step is going to be finding the second pivot position, which is this one right here, and we are going to use it to remove everything below it, specifically this 2. In order to do that, we subtract 2 copies of this row from this row, and we end up with a last row of zeros. To get the proper reduced row echelon form for A transpose, we need to swap out some rows and put all the rows of zeros at the very end. Since we have pivot positions in the first column and the second column, this means that the first 2 columns are pivot columns and this one is a free column, which means that x3 is a free variable. In order to find the solution for the left null space, that is A transpose times x equals 0, we look at the first equation, which gives us x1 plus x3 equals 0, which means that x1 is equal to negative x3. Similarly, we look at the second equation, which gives us x2 plus x3 is equal to 0, which means that x2 is equal to negative x3. Our solution for the left null space is going to be the vector x1, x2, x3, which is equal to the free variable x3 times the vector minus 1, minus 1, 1. This means that the basis for the null space of A transpose is simply the vector minus 1, minus 1, 1, and therefore the dimension of the null space of A transpose is equal to 1, which is exactly the number of vectors in the basis.